Hello viewers, how are you today? Welcome to Ask Me IT. I'm just kidding. I'm not Indian. But seriously, welcome. In this video, I will cover what IP addresses are and how we assign IP addresses to devices in our network. In part 2, I will cover subnetting. In part 3, I will explain what supernetting is. Alright? Now, the IP found at OSI layer 3 is responsible for end-to-end delivery of data, or packets to be specific, between computers in an IP network, for example, the internet. To find a path between two computers in a large network, such as the internet, computers must be uniquely identified. To do that, the Internet Protocol defines IP addresses, which are a unique 32-bit sequence of ones and zeros. For example, this long sequence of ones and zeros is a valid IP address. For the ease of use, IP addresses are represented in a form called the dotted decimal format, because understanding, as you can see, this long sequence of ones and zeros is difficult. The 32 bits of the IP address are grouped in 4 bytes or 4 octets, limited by dots and transformed into the decimal form because it is simpler to use decimal number instead of long sequence of ones and zeros, as I said. So for example, the IP address shown here is this one, which is the previous sequence of ones and zeros we have seen in the last slide, can be changed into decimal format by grouping the bits into 4 groups, which are 8 bits long each. Now, after changing each octet to decimal, we add a dot between the octets, and then we find this dotted decimal format. Alright, so they are equivalent, but this is easier to use, so usually IP addresses are formulated in the dotted decimal format. In order for one interface to communicate in an IP network, it must have an IP address. So actually, when we say assigning IP address to a device, we are talking about assigning an IP address to the device's interface, specifically to its network interface card. Now, two hosts that have the same IP address in the same network will conflict with each other because they should have a unique IP address, and only one or none of them will work on the internet. An IP address can be statically configured on a device by assigning an interface a fixed IP address in the dotted decimal format, or we can assign IP addresses dynamically too. So there are 2 ways of assigning IP addresses, static and dynamic. Using the static way, the host has a static IP address and will use it until the user changes it. Now, servers, routers, and network printers should be assigned static IP addresses. Also, if a network is small, statically assigned IP addresses doesn't make it difficult for the administrator to keep track of computers because it's a small network. The most popular protocol for dynamic IP address configuration these days is DHCP, which stands for Dynamic Host Configuration Protocol. So, rather than assigning IP address statically, we can assign IP addresses dynamically using this protocol, DHCP. Configuring a DHCP involves a few simple tasks like specifying a range of IP addresses that can be assigned to clients, assigning a DNS server IP address, and the default gateway for the clients. So what we do in DHCP is we just specify a range of IP addresses that can be assigned to clients, right, to the users in the network, and we assign a static IP address to the DNS server and the default gateway. This is very simple to set up when administering a large LAN because you don't have to set up static IP addresses on each computer or on each client. The DHCP server does all the work. An IP address has 2 parts, one that specifies the network that is in and one that uniquely identifies it in that network. So the 32-bit long IP address has 2 parts, a part that specifies the network that the host is in and the rest that uniquely identifies that host in that network. The first part is called the network part of the IP address, and the second part is called the host part of the IP address. To identify the 2 parts of an IP address, devices use a network mask or net mask for short. Network masks have the same format as IP addresses, 32 bits, and have the bits in the network part of the IP address set to 1 and the bits in the host part set to 0. For example, if you find computers from 192.168.1.0 to 192.168.1.255 on a network, it means that all computers have the network part 192.168.1, which is common for all computers, and the rest will be the host part. The last octet is the only difference, right? So from 0 to 255, but the rest is common. So the common one, that is what we call the network part. Now the network mask, the net mask in this case is, as you can see, this is the common one. 192.168.1 is the common one for all hosts in the network. So the net mask for this network will be all ones for all these 3 octets and all zeros for the last octet in binary, and 255.255.255.0 in decimal form. So this is the net mask of this network. So all ones are the network part in the IP address, all zeros is for the host part of the IP address. To accommodate different size networks, IP addresses are divided into groups called classes, identified by the leftmost bit or sequence of bits. So in other words, what we are saying is IP addresses can have different number of bits for the network part and different number of bits for the host part. The classes are called class A IP address, class B IP address, and so on and so forth until A. And this process is called classful addressing. So when we see in detail what these classes are all about, in class A, the leftmost bits are 0 and then variable. So whatever, they can be 0 or 1. The start address for class A is all zeros, because what we are saying is this is fixed, it's always 0. The rest can be anything. So if, for example, we set all of the rest bits to 0, we will have the starting address of 0.0.0.0. And the end address for class A is 127.255.255.255, which is 0 and the rest all set to 1. In class B, the first 2 bits are fixed to 1 and 0, as you can see, and the rest bits can be anything. Now, after setting the first bits to 1, 0, if we put 0 in all the rest bits, we get this value 128.0.0.0, which is the smallest number in class B IP addresses. If you assign 1 to the rest of all the bits, and of course 10 is always fixed, so the rest 30 bits, by setting them to 1, we will find this number. First octet will be 191, the rest octets will be 255, because groups of 8 ones is 255. In class C, we have the first 3 leftmost bits set to 110. The rest bits can be anything. So if we assign 0 for the rest bits, then we will find this start address 192.0.0.0. And if we put 1 to the rest of the bits, we will find this number 223, 255, 255, 255. Similarly, in class D, we have the first 4 bits set to 1110. Now, the smallest number in this class is all zeros except these 4 bits, which will give us 224.0.0.0. And the biggest number in class D is 239, 255, 255, 255, because we have these 4 values fixed, and assigning 1 to the rest of the bits will give us 239, 255, 255, 255. Class E similarly has its leftmost bit set to 4 ones. If you put the rest bits to 0, we will find 240.0.0.0. If we have assigned 1 to the rest bits, we find 255, 255, 255, 255, because all the bits will be 1. Alright, the fixed one is 4 and the rest 28 bits. If we set them to 1, we will find this number. So as you can see, class A ranges from all zeros to 127, 255, 255, 255. Class B ranges from 128.0.0.0 to 191.55.55.55. Class C ranges from 192.0.0.0 to 223.255.255.55. Class D ranges from 224.0.0.0 to 239.55.55.55. And the last class of IP address, class E, ranges from 240.0.0.0 to 255.255.255 and 255. When we further investigate each class, we said the first bit of the first octet is always set to 0. Alright, so it's fixed. Always the first bit of the first octet is 0 in class A IP addresses. Because the first bit is 0, we have 7 bits, right? From the first octet, we have 7 bits. Now, if we set, as we said before, if we set all zeros, we have 0 in the first octet. And if we set 0 and 7 other bits to 1, we find 127, i.e. Class A usable addresses only include IP starting from 1.x.x.x, x being any, to 126.x.x.x only. Okay, so the range of usable IP addresses for Class A, IP address that we can assign to computers, ranges from 1.x.x.x to 126.x.x.x only. The IP range 127 is reserved for loopback IP addresses. I think what it means is we can send a packet to its source or to the sender if, for example, we cannot find the destination, right? So we don't use that for assigning clients. The default subnet mask for Class A IP address is 255.0.0.0. In other words, what it means is we can only use the first octet to identify the network, and we can use the rest of the octets or the 3 octets, 24 bits, for identifying hosts in the network. Which implies that Class A addressing can have 126 networks, which is 2 raised to 7 bits. We use 7 bits because 1 is fixed, minus 2 raised to 7 bits, which is combination of 7 bits in binary, which will be 2 raised to 7 minus 2 because we have 2 IP addresses. We don't use all zeros and all ones, right? So this is 126 networks. From 128, we use only 126 networks. And this much hosts, which is 2 raised to 24, because we use 3 octets, which is 24 bits, 2 raised to 24, minus 2. Again, similarly, we don't use first and the last IP addresses to assign to clients in the network. An IP address which belongs to Class B has the first 2 bits in the first octet set to 10. The default subnet mask for Class B is 255.255.0.0. So in contrast to Class A, Class B has more bits for the network part, and it has 2 octets or 16 bits for the host part. Class B has 2 raised to 14 network addresses because the 2 bits are fixed 10, so we have 2 raised to 14, not 16 bits. This much network address and this much host addresses, which is 2 raised to 16 minus 2, because again we are deducting the IP address we don't use to assign to clients in our network. The first octet of Class C IP address has its first 3 bits set to 110, as we have seen before. The default subnet mask for Class C is 255.255.255.0, which is 24 bits for the network part, and we are only using 8 bits for the host part. So now Class C gives 2 raised to 21 network addresses, because again we are not using all 24 bits because we have 110 fixed, so 21 bits, 2 raised to 21 network address, and 2 raised to 8 minus 2 host addresses. Similarly, we don't use the first and last IP addresses. They are reserved, so we have 2 raised to 8 minus 2, or 254 host addresses. In class D IP addresses, the first 4 bits are fixed to 1110. Class D is reserved for multicasting. In multicasting, data is not destined for a particular host, but it is destined for multiple hosts. That is why there is no need to extract host address from the IP address, because there is no specific host, just group of hosts. So data is sent to group of hosts, not a specific host. And class D doesn't have any subnet mask because we don't have specific host address. In class E, we have 4 ones fixed. The leftmost bits in class E are 4 ones. This IP class is reserved for experimental purposes only, for research and development or study. Like class D, this class 2 isn't equipped with any subnet mask. It doesn't have a subnet mask. Alright, thank you for watching and stay tuned for part 2 for subnetting. So subscribe and turn the notification bell on so that you will be notified when I upload the next video. Thank you for watching. Bye.